Okay, let's get started. Today is our great pleasure to welcome Professor YuhuaZhu from UCSD. So Yuhua now is assistant professor at the Department of Mathematics, and also she holds a joint appointment in uh, Harisegro Data Science Institute. Previously, she was a postdoc at the Stanford University, and she received her PhD in mathematics from University of Wisconsin-Madison. Her work mainly focuses on the interface of the PDE and machine learning, including using PDE to provide a theoretical interpretation to existing stochastic optimization algorithms and the reinforcement learning algorithms, and also using numerical techniques to improve machine learning algorithms. Today, Yuhua is going to tell us a continuous in time limit for Bayesian bandits. Yuhua, please.
Yes, thank you very much for the introduction. Thank you so much for the invitation. And it's my great pleasure to present my work here. It's a joint work with Lexing and Zach at Stanford. So first, I'm going to talk about multi-arm bandits, which is actually one kind of sequential decision making. And it has a lot of applications in real life, such as recommend advertisement, products, movies on Amazon and Netflix. The multi-arm bandits is a very frequently used tool to decide which movies or which product to recommend to the customer. And also like decide dynamic pricing in Expedia and also dynamic treatment in medicine. So first, what is this multi-arm bandits? What is this multi-arm bandits? So first, for example, we have $100 and we have two slot machines in front of us. And it takes $1 to play one of them once. And we know that this two slot machine, the reward is following the normal distribution with a known variance 1, but with an unknown expectation nu. So what is the best strategy to get the maximum total reward out of this $100? So think about this problem. You're probably going to come up with a very naive strategy, which is we pull each machine 25 times, and then we will get empirical mean, mu1 hat, mu2 hat. And then we pulled with a larger empirical mean for the rest 50 times. So it sounds like a very reasonable strategy. However, there are two problems of it. Think about the case where the first machine, the expectation is 10. The second machine, the expectation is negative 10. And then one actually do not need to pull 25 times to figure out that the first slot machine is actually much better than the second one. So basically, in this case, you waste too much time on an obviously wrong arm. So this case is you explore too much and exploit too little. And the second case is the opposite one, where the expectation of this two slot machine is very close to each other. So it's very possible that after polling 50 times, you will find the empirical mean of the first slot machine is less than the second one. So you are playing the rest 50 times on the wrong arms. So in this case, you are actually spending too little time to differentiate the two arms. Okay, so multi-arm bandits is really just a trade-off between exploitation and exploration. So here are some better algorithms. The first one is called upper confidence bound, which is introduced by Lai and Robbins in 1985. So what they do is they have a point estimation, mu hat, about the expectation based on history data. And then they construct a confidence interval. And then they use the upper bound of this confidence interval as the criteria to decide which arm to pull. And if we look at, this arm, this upper bound, we will see this is actually empirical mean plus an extra term. And this extra term is inversely proportional to the number of poles of the case arm. And you can imagine when this empirical mean of arms are close to each other, then the second term will dominate, which will automatically lead to pooled arm which has been less explored. On the other hand, if the empirical mean has a very significant difference, then the second term will not make a big difference on this upper bound. So this is the automatic balance between exploration and exploitation. Another very popular method is called Thompson sampling. So what they do is, based on historical data, they construct a density estimation about the expectation. And then they sampling expectation based on this posterior measure. And then they compare at the pooled arm, which has the biggest sample from this posterior measure. So this is also a very good exploration, a balance between exploration and exploitation. So to summarize, both methods at each round I, they will give an explicit policy based on either point estimation or density estimation about expectation. The question is it optimal? So before we just answer this question, let's first define what is the optimality in multi-bandit problem. So the general setting is the following. We have k arms, and each arm will follow a probability density function. The reward will follow a probability density function that is determined by the environment nu, which is usually unknown to us. And we have n total poles, which we call horizon n. And at each round I, we are going to pull arm AI according to policy pi I. And it will give us a reward xi. And the policy pi I is a mapping from the history data to a probability mass function on the arm space. Okay, so the general goal here is we want to maximize the expected cumulative reward. Okay, if we look at this cumulative reward, at round J, the expectation of your reward actually depending on two things. The first thing is which arm you pull, which is determined by your policy. The second is which environment you are in. So in other words, this expected reward will depending on your policy and the environment nu. So think about this maximization problem. The optimal policy is obviously pulling the best arm, which has the biggest expected reward for all these k arms all the time. However, this is unrealistic because this environment nu is not priori known to us. So this is not a well-defined maximization problem, optimality. So what people do is the following. They define an expected regret. And this expected regret is what? So after we pull n times according to our policy pi, we realize, oh, we actually should have pulled this best arm from the beginning. And then what is regret about this policy? And people prove that for any reasonable policy that you do not know the environment priori, the lowest regret you can achieve is order log n. Okay, and people prove that the UCB, upper confidence bound, and the Thompson sampling can achieve this lower bound in an order log n. And in this sense, UCB and Thompson sampling are asymptotically optimal in this sense. However, we can see that we have a constant C here, and this constant C could be very large. So question is, can we have another optimality definition? based on the estimation of the environment mu hat. For example, we have a density estimation based on the Bayesian rule, or we have a point estimation, which is the empirical mean. So based on these two estimations, can we define an optimal policy? So here is the second definition. First, as we just talked about in the previous slides, this definition of expected reward is not well defined because we do not know the environment mu. But based on the density estimation about this environment mu, we can actually, at each round I, so we can actually integral this unknown environment with respect to this density estimation. And then our expected reward is going to be independent of the environment. And similar to the point estimation, we can replace this environment mu by the point estimation mu hat. And the optimal policy based on this definition, we call it estimation-based optimal policy. Okay, so now we have two definitions of optimality. And is this estimation-based optimal policy a good definition of optimality? So how, in other words, the optimal policy coming from this optimization problem, will it have a better performance than UCB and Thompson sampling, even if we are measuring the performance in definition 1? Okay, the answer is yes.
Sorry, okay. May I ask a question?
Yes, please.
Sorry. So based on the definition 2, you said you need to estimate the rho I for the unknown environment. Is that easy to estimate, or?
Yes, it's a good question. So, for example, using Bayesian rule, and for the normal distribution, ballooning distribution, we always have explicit formula for the posterior measure. Yeah, in that case, it's not a difficult problem. But of course, if we are dealing with some more complex probability density function, which we do not have explicit formula for posterior measure based on history data, this is not necessarily difficult, not necessarily easy task. But this thing is actually, you also have that for Thompson sampling, because you also need the posterior measure for Thompson sampling. I see. Yes. So here we just assume we already have that as a step.
You just assume. But in practice, the density could be could be very, very complicated.
Yes, you are correct.
Thanks.
Okay. So, so here is example where we measure our performance by this expected regret on a one-armed bandit problem. The one arm follows the ballooning distribution with the unknown probability mu, and another arm which will already have a deterministic reward. So this problem is, when should we pull the unknown arm? And here the blue line is obtained by our optimal policy based on the point estimation or the density estimation. And we compare this expected regret with UCB and Thompson sampling. And we can see we always have lower regret than these two methods. So an estimation-based optimal policy can perform better than UCB and Thompson sampling, even in terms of expected regret. So after an extensive literature review, we find that this definition is actually exists in it's actually already proposed in 1956 when this multi-arm bandit framework is proposed. And it actually dominates the research on the bandit problem from 1950 to 1980. And this framework is, of course, only based on the Bayesian framework. And here we also can have similar things for the point estimation. But there's one big difficulty of this optimal policy based on the density estimation, which is high computational cost. So in order to find this optimal policy, for a k-armed problem with n horizon, the computational complexity is order n to the 2k, which you can imagine when k or n is large, this could be very large. The only breakthrough in the literature is called Giddens index, where the computational cost is reduced to order k times n squared. However, when n is large, this is still pretty large. Second, it can only apply to discounted cumulative reward. That is, you discount the future reward by gamma to the i's power. So this problem, and gamma is a constant that's strictly less than 1. So this problem, this discounted problem is actually easier than undiscounted problem. So it's actually a 60-year-old problem, how to reduce the computational cost for this undiscounted cumulative reward when the horizon n is large. And so today we're going to tackle this computational cost problem by using PDE limit of this estimation-based optimal policy. But before we go to the PDE limit, let's first look at why we will have such a big computational cost for finding the optimal policy. Let me explain this by looking at this illustrative example, which is about an one-armed bandit problem, where one arm follows the unknown arm follows the ballooning distribution with an unknown probability nu. Therefore, the expectation of this first arm, this unknown arm, is actually depending on this nu, which is the expectation is exactly equal to this nu probability. And the second arm is a deterministic arm, which we have reward 1/2. Okay, so here's the setting. At the beginning of round I, we already have an estimation about the expectation, which could coming from a point estimation nu hat or density estimation rho nu. And by integral over nu, you can also have the expectation of mu hat. Okay, and we have some history data, which represented by the cumulative reward of the unknown arm up to round I minus 1, and the number of pulls for the unknown arm up to round I minus 1. And now how to compute which arm should we pull based on the history data. So what we do is following. We construct a function omega, which represents the optimal expected cumulative reward starting from round I until the final round n. So this optimal cumulative reward can be separated into two parts. The first part is the expected reward at this round I. The rest is the optimal cumulative reward starting from round I plus 1. So the second part is related to omega I plus 1. And if, for example, at this round I, the second arm, which is the deterministic arm, is pulled, then this cumulative reward should equal to 1/2, which is the reward we get at this round, plus all the reward starting from I plus 1. If the first arm, the unknown arm, is pulled, then the cumulative reward should be mu 1/2, which is the reward at this round based on our estimation, and these two terms, which because after we pull in this arm, we will have probability nu hat to have reward 1, which means at the next round, the cumulative reward S will becomes S plus 1. And this term means that we will have 1 minus nu hat probability to have reward 0 at this round, which means at next round, the cumulative reward S will becomes the same. Okay. And the best, the optimal reward would be which one is larger. And the optimal policy would pull the one that has larger optimal cumulative reward. And by definition, we can set the cumulative reward after round n is equal to 0. And we can derive each round, the optimal policy at each round I from backwards. Okay, so here's the algorithm to derive the optimal policy. Our optimal cumulative reward at round I will depend on the optimal reward at round I plus 1, and it depends on the rewards function at S, Q, and S plus 1, Q plus 1, and S and Q plus 1, which means that if you want to calculate the function's value at round I at S and Q, you need function's value at round I plus 1 at these 3 points. And then in order to calculate these 3 points, we need to go backwards until we reach the final round where we know the function value is equal to 0. So because this backward induction for calculating the optimal policy, the total computational cost for this one-armed bandit problem is order n squared. N is the total number of poles, n is the horizon. And in general, k-armed bandit problem, the computational cost is going to be order n to the 2k. And that's why the computational cost is pretty high when we're calculating the optimal policy. Okay, so can we reduce the computation cost when n is large? The answer is yes, and the solution is through PDE limit. So let's first see why can we derive a PDE limit. At least for this illustrative example, we can explicitly write down how to calculate the optimal cumulative reward for at round I based on the function's value at round I plus 1, following this formula. And the key point here is to do a rescaling of the round I and the history data S and Q. So first, we rescale the round by 1 over n. And the reason why we want to rescale it by 1 over n is because you can imagine previously we have n rounds, and after we rescale it by 1 over n, this n rounds will shrink into the interval from 0 to 1. And then if the number of poles, the horizon n goes to infinity, you can imagine this time will become continuous. Accordingly, we'll also rescale this number of poles by 1 over n, and the cumulative reward by 1 over n. And the cumulative reward for the expected cumulative reward, optimal cumulative reward, also rescaled by 1 over n. Okay, so after this rescaling, we will end up update rule for this rescaled optimal value function. And here I did nothing, just rewrite this formula in another form with respect to the new rescaled parameters. But if you look at this equation, you will see this is actually the first order numerical scheme of this following PDE. If you look at the first term, you can see that this is basically a partial derivative with respect to time. And this term is basically a partial derivative with respect to S. This is like a partial derivative with respect to Q. And that's why we get this continuous form for PDE. And this PDE is actually a Hamilton-Jacobi-Bellman equation. And what's good about this HJB equation is that the optimal policy is actually free if the value function v is obtained. So if we can get a solution for this PDE, then the optimal policy will be calculating this Hamiltonian and find the maximum dimension and then you pour that on, and that is your optimal policy. Okay.
So, but when you solve this HJB, the how should I say? It's a not initial value problem, but the terminal value problem, if I can call that, right? So you hope you have some faster solver to solve this HJB with terminal value problem, then use that to. But then you still need to discretize your PDE. Then you just call some solvers for the HJB. Is that what you want to do?
Yeah, so there's two cases. If we have exact solution, then we do not to solve it numerically.
Oh, of course.
Yes, so I will mention later that some frequently visited multi-bandit problem, we actually have exact solution for this HJB equation. And the second is, even if we need to, like solve it from backwards, we need to divide it in time, right?
Yes.
There's time mesh, but however, this time mesh is independent of your horizon n. So this only depends on your time mesh, which is how you divided your time interval. That is independent of this horizon n. So this could be, for example, we are solving a problem for horizon n is 1 million, but we can divide this time horizon by just 100, which is already a pretty good estimation for the solution.
I see.
So that will, yes, that will actually decrease the computational cost.
But the other thing is, speaking about PDE, right? You have the spatial variables, which is the S and the Q here, right? But the conventional solver cannot handle for the large dimension, which you may have large dimension in your case. So
yes.
Then
yes, it's a very good
conventional
question.
solver cannot be applied, right? There's some optimization, like extent also they have some using Hoffman's formula to do something.
Yes.
So that could be the way, I guess. But anyway.
Yes. It's very correct. So I'm actually currently working on collaborating with their group on how to solve the high dimensional problem.
Oh, I see. Okay.
Yes.
They use some optimization algorithm to solve the HG.
Yes, right. Yes. That will be much faster than like finite difference method.
Well, I mean, Heidi cannot. But the thing is, their approach can only see any given point if you're looking for the value, right? If you're looking for the whole domain, the value on the whole domain is still the same complexity, right? Because that given point they can write down this as some kind of optimization. That's all, right? If you visit everything, I'm not sure in your context, do you need to visit every point in the domain or you don't?
It's a very good point. So yes, if we want the solution for the whole domain, the complexity is impossible to reduce.
Exactly.
However, we do have some structure of the trajectory here.
Okay.
Because it's actually following some underlying distributions, right? So the trajectory will only follow some kind of trajectory.
So you have some lower dimensions.
Yes, so it can be reduced to a low dimensional problem.
Interesting.
Yes.
Thanks.
Very good question. So let's first see how this convergence rate, how close is the rescaled optimal cumulative reward and the solution to this HJB equation. So here I plot the arrow between these two terms. We can see that as n increases, this arrow will decrease in a very fast rate. And we can see that for n equal to 100, the arrow between these two terms is already pretty close to pretty small. Okay. So this up to now, it's only for the illustrative example for this one-armed bandit problem. And for the general case, let me present you we also have the PD limit. So first, for the general case, the optimal cumulative reward, omega, can be represented in this form. For example, given a point estimation you had, we can represent this by the first term represented the expectation at this round, And here is the expectation after round I plus 1. Similarly, for if we are given a density estimation. So this is formula for the how to calculate the optimal cumulative reward. And for the PD limit, here is the setting. So we have we use the S and Q to represent history up to round I, and SQ represent for the cumulative reward of each arm up to round I plus I minus 1. Q is the number of pulls for each arm up to round I minus 1. And density estimation, assuming that at each round I, we have a density estimation, row I, or point estimation, new several frequent visited multi-arm problem. Actually, the exact solution exists, can be explicitly obtained for this HJB equation. Okay, let's see the first one. So first, you probably know that HJB equation is actually the solution of a stochastic optimal control problem. And for our HJB equation, the corresponding optimal control problem is this one, where the objective function is basically the cumulative reward starting from time t. And the state function S and Q is actually following a stochastic differential equation, where the drift term is determined by the first moment and the policy. The second diffusion term is determined by the second moment and policy. And the number of poles Q satisfy an ODE, which is determined by your policy. Okay, and the regularized version is basically, it's a very commonly used trick in finding optimal policy, where you just add a regularized term with respect to this policy. So this is the optimal control problem, where you add this regularized term in your objective function. And accordingly, you will also have a regularized version of HJB equation. And in this case, you can actually calculate the optimal policy, which is proportional to your Hamiltonian. And there are several advantages about this regularized version. So first is, for the previous one, the optimal policy is a deterministic policy, where we choose the optimal arm who has the biggest Hamiltonian, right? But for this one, the optimal policy is actually a stochastic policy. So it's less sensitive to the perturbation. Second, the value function, then it becomes smooth. Previously, the value function, usually you will have a viscosity solution, which is not always differentiable everywhere. But now, after add this regularized term, and the value function is smooth, which means usually it's easier to numerically solve it. Another implicit advantage is this regularized term, which end up a stochastic optimal policy, will encourage more exploration. This is especially useful when your estimation at round I is not very good. I will show you some example later in a numerical experiment when you don't have a very good prior estimate in your Bayesian framework. After adding this regularized term, it will give you a better policy. Okay, so this is the regularized version of the estimation-based optimal policy. And then how to have a more efficient algorithm based on the solution to the HJB equation. So the idea is also simple. So first we solve this HJB equation, and by solving this HJB equation, the computational cost is actually order 1, which means it's independent of this horizon n. And as I mentioned, when you have exact solution for this HJB equation, solving this HJB equation, the computation cost is 0. And if you have numerical method, it's based on what kind of numerical method you use. That is your computational cost. Okay, but both way, it's independent of this horizon.
Sorry, may I clarify? So the n and k, which is the size of the, if you discretize the HJB, if you don't have a closed form solution, the k n and k is going to corresponding to the size of the discretization of the t and s and q. Which one was corresponding to which one?
Yes. So this k is basically the dimension of your spatial parameter.
Okay.
Yes. K, yes, K. For example, you have two arms. Then use the numerical method. If you divided the time interval by n,
Yeah.
then the computational cost will be n to the fourth power.
But if you, let's say, if you're doing this in a high dimension, the 2D, so the number of the variable, when you solve the HJB, the number of variable exponentially depends on the size of the S and Q.
S and Q, yes. S and Q, the dimension of S is K, depends
Okay.
on how many arms you have. And the Q is also has the same dimension. So if, for example, you have two arms, then the dimension of your HJB equation is 5.
So you
T,
still have some kind of exponential dependence in terms of K, not other one. If you want to numerically solve HJB, is that what you mean?
yes, correct, correct. So here I say order 1 is just saying it's independent of this
I
n.
see.
Yes.
Oh, I got it. That's true.
Yes.
Oh, yeah, that's true. Because time, you just multiply n when you do the
Yes.
PD.
Yes,
Okay,
yes,
next.
correct. Yes, correct. Okay. And after solving this HJB equation, we will have an explicit optimal policy pi by the optimal policy from that HJB equation, which is explicit, which can be explicitly obtained. And then at each round I, what we do is at that round I, we will have the data. We'll arrive at some state, and then we rescale this state to the rescaling factor f hat and q hat and t, and then we use the optimal policy to polling our arm. Okay. And as I said, if we can have some exact solution, then we don't need to worry about how to numerically solve this HJB equation. And it turns out actually several pretty popular multi-arm-banded problem has exact solution. So there's two special cases. The first is each arm follows the ballooning reward. So basically, the arm K give reward gamma with probability nu K, and give reward negative gamma with probably 1 minus nu K. And in this case, if we set the prior estimation as a beta estimation, then we will see that the first moment mu hat will in this form, which basically is the rescaled cumulative reward plus a constant over a rescaled number of poles plus a constant. So it's similar to a empirical mean with some modification. And the second moment sigma hat is going to depend on your Fm and the value of your gamma. And for another very frequently visited multi-banded problem is following the normal distribution. For each arm K, it follows normal distribution with known variance sigma but unknown expectation. It has the same first moment and second moment. It has a similar form of the mu hat and sigma hat. And here's the theory. As long as the first moment is in this form, for the unregularized HJB equation, we will have an explicit policy, which will only depend on how large is your mu. And to be more specific, for example, if we apply this to this one-armed bandit problem, and you will end up this policy. So you are going to pull the arm who has a bigger value of the empirical mean plus some term that is inversely proportional to the number of poles, which you can see it has a very similar form as UCB. And for the regularized HJB, you have similar conclusion. As long as this first moment has this form, you always end up optimal policy that is proportional to this exponentially proportional to this first moment. And this also has a similar form as a very popular multi-arm bandits, which is called the tempered greedy algorithm. Okay. So finally, let me summarize this talk by some numerical experiments. The first numerical experiments show you the difference between the optimal policy based on the HJB equation and the actual optimal policy, and the optimal value function based on the HJB equation and the actual optimal cumulative reward. So the arrow actually decay pretty fast as the number of poles n goes to infinity. And here we can see with different rescaling, we actually end up different arrow. Although the decay rate is similar, but if we use bigger rescaling factor n, which means you actually miss more data, you end up a deterministic optimal control problem, and then you will have a bigger error. If you rescaling with a smaller factor, which is square root of n, you end up a stochastic optimal control problem, which you basically have more information about your multi-arm bandits, you will have a smaller error. Okay, but still, even if you use n when you have 10 to the third, when n into 10 to the third error is still quite small. So both are very good approximation to the original problem when n is large. And also, I try to this plot shows you the difference between the numerical solution to the HJB equation and the original optimal policy and optimal value function. This also have a pretty nice decay. The only difference is that if you use a less accurate numerical algorithm, for example, you use time discretization n equal to 50, the arrow won't decay. The arrow won't decay after you reach some point, because then the numerical arrow will dominate the difference between these two terms. But if you have a more accurate numerical algorithm, the arrow will still decay pretty fast. Okay, and here's the performance of the optimal policy based on the HJB equation. So here, this case where we can actually calculate the exact solution explicitly, so we can use this to apply to very high dimensional multi-arm bandit problem. Even for k equal 20, there's no problem for that. And we can see this yellow line is the optimal policy based on our HJB equation, which we almost have the smallest regret. The only thing that is not work very well is when our prior estimation is not that good. Then we are probably will have a little bit bigger regret than the UCB. Because our method is based on the Bayesian framework, which highly related to your prior estimation. And when your prior estimation, assuming your expectation is actually near 0, but your actual expectation is -1, so we will have a little bit worse regret than the UCB. But in general, we always have better regret than Thompson sampling. Okay. And this is a case where we cannot obtain the exact solution, but based on the numerical solution, we still have better stable regrets than UCB and Thompson sampling. We can see that this yellow line, we always have we always have smaller regret than Thompson sampling. Compared to UCB, so we are more stable. So UCB in this cases will have very bad regret, but we always have the smallest maximum regret in these two cases.
What's the dimension of this one again?
This one is 2-dimension.
Okay. Okay.
Yes. So basically, the function's dimension is 5.
Okay, fine. But when you solve HJB, you discretize the domain. That's 2-dimension.
No. When we solve the HGB equation, we discretize domain, which is 5-dimension. So the
You have to
time.
use some very sparse grid, or how do you solve PDE in 5-dimension?
Yes, it's a 5-dimensional problem because we have two arms which has S and Q that is 4-dimension, and then time is 5-dimension.
Sure.
Yes, so here we use 100 time discretization,
Yes.
which the computation cost is still doable.
Wait, but then the spatial dimension you have 4, right? You have a 1-dimension for the time, 4-dimension for the spatial, for that HJB. That's already very.
Oh, I'm sorry. Yes, we have 2 arms, but here the spatial dimension is actually 2. I'm sorry.
Okay.
Because it's a linear binary problem. Yes, we only have mu, which is in 1 dimension, so it's
okay.
Yeah.
So it's a 3D problem.
Yeah, 3D problem.
That's still affordable. Okay.
Yes, correct. And as I mentioned that when you have a worse initial prior measure based on the Bayesian framework, we can actually use the regularized version of the HJB equation to get a better optimal policy. And here is an example where if we have this lambda is a regularizer constant, and if we have a bigger constant, we have smaller grad. I just want to show you that the regularized version has an advantage when our estimation is not that good. Okay, and here's some related work. So there's also some work at Stanford. They derive continuous limit for Thompson sampling algorithm, and also there is a work by a Columbia group in economics. They derive a continuous limit for Bayesian optimal policy, but the setting is only works for 2 possible only if the environment include 2 elements. And our work is much more general. We can work on continuous environment, and it also reduced the computation cost and is large through the PDE limit. And here is just some ongoing work in open problems. I want to mention a little bit about these open problems. So there are some open problems when, for example, the number of arms k goes to infinity. Can we derive any like mean field control problem? Because currently, if you cannot solve this HGB equation exactly, you need to solve it numerically. Then when k is large, the computation cost is actually still pretty large. So is there any better way than when k is very, very large, we go to a mean field limit, then we'll probably have some better algorithm from the mean field limit point of view. And also, what is convergence rate for this HGB equation? And does there exist a PDE limit for adversarial bandits or contextual bandits? Yeah, so these are the open problems. And then that's it for my talk. Thank you.
Thanks very much. Very, very interesting talk. For the audience, any questions?